original team of the Allen Hills meteorite, and which came to public attention in 1996, which contained evidence for past life on Mars. It was very controversial. The debate on that meteorite is going on to this date. So Dr. Gibson is going to talk about that and about the latest results. Now, I must say this, that those of you who are here are extremely privileged, because there's part of this talk that we will not be able to broadcast because it's embargoed, because it's scheduled for publication in the fall. And it's not yet ready to go out in a fully public way. So, but those people who are here are going to get a sneak preview of some stuff that has yet to be made public. So, and to those who are online, you should understand that at a certain point in the talk, we will ask the videographer to turn it off.
We worked it out.
You worked it out?
Right. We worked it out.
All right. So just expect that. That's just going to happen. And I should add one other thing, that a number of the developments that occurred around the Allen Hills controversy are extremely interesting. Some are even extremely funny. And Dr. Gibson at the banquet on Saturday night is going to give a short presentation on some of that aspect of the Allen Hills controversy, which is really quite something. But today he's going to talk about the science. So without further ado, Dr. Gibson.
Thank you for coming. I'm very pleased to be able to present what's been going on over the last few years. And our research team has not rolled over and played dead. We've been working very hard, very discreetly. We've been publishing peer-reviewed manuscripts. We've not taken all the time to answer all the snippets that's been directed at us, because the only way to solve these things are through good, solid science. And I'm very happy to say, after 18 years, the data that we presented in August of 1996, that data still stands and has not been refuted. The controversy is the interpretation of that data. But no matter what happened, we changed the terrain that all of us worked upon. What I'm going to be talking about today, I'd like to acknowledge my colleagues that have worked on it with this: Dave McKay, Kathy Thomas, Simon Clement, Sue Wentworth, Lauren White, and Colin Pillinger. Now, we lost Dave McKay in February of 2013. A major loss to our team, his colleague, a great researcher. In May, we also lost the gentleman whose team reported the first indigenous organic material in Martian samples, the Martian meteorites. Colin Pillinger and his team at the Open University reported in 1989 organic matter in the Martian meteorite 79001. Colin and his team should continue to receive credit for this. A great individual, a major loss to the European Space Agency's exploration program in Mars research. The lander, which in November will land on the comet, is Colin's instrument. It has a mass spectrometer on it. I'm pleased to say that instrument is receiving data right now, and we'll know the organic composition in November as we contribute to Colin. Mars, that's why we're here. The interest has been, does this body contain evidence of living systems, present or past? Now, let's set the stage in 1996. The Office of Management Budget had told NASA that it was to reduce its space science budget $6 billion. $6 billion over a 5-year period. The Mars exploration program is in disarray. Failures that have been occurring. Between 2,000 and 3,000 layoffs have been announced at JPL. Our Allen Hills announcement in August of '96 changed things. We're really happy to say that that $6 billion number was restored and the budgets were leveled out for 5 years. We had programs, the NASA astrobiology institutes were created, NASA's Origins program, and also the Search for Life programs were added to the NASA program. We've had a very successful Mars exploration strategy program since then. But Mars has been under the microscope, whether it's been in orbiters, landers, rovers, or even samples. All these have contributed to our knowledge. Meteorites from Mars are really poor man's space program. They're delivered to us at no cost. We have between 72 and 76 of these in hand. We have more than 96 kilograms of Martian samples in our laboratories today that's available for study. Stop and think about this number. The number that's being planned for our sample return mission is in the 1 to 2 kilogram size quantity. We have 40 to 50 times that number already in the hands of the laboratories on Earth. But not all of those samples are suitable for study because they've been terrestrialized. They've laid on the Earth, they've been contaminated. Our criticism, our team's work, for what you've done is contamination. No, you have to understand contamination and separate it out from the indigenous organic carbon components that are present in the sample. Now we do know from studying the meteorites, the Martian, we have samples of varying ages, from 4.1 billion years ago up to 165 million years, across the span of Mars, when it was warm and wet to the period of dry and cold. We have the early Martian crust, a sample from the southern highlands, down to secondary alteration products that were occurring in the meteorites that we collected. We now have a few samples that may be sedimentary rocks from Mars, but unfortunately they're not suitable to really study the current surface of Mars because they've been on the Earth's surface too long. We have subsurface samples of most of the 70-some samples we have because the energy that's required kicks out sample from a tenth of a kilometer or so beneath the surface. So any organic matter in there could be preserved or not been subjected to ultraviolet radiation or oxidants that may be present. Now in particular, we've been concentrating on 4 samples. From the Allen Hills, 84001, to the Nocla, which is 1.3 billion years old, and had water percolating through it at 1.3 billion. We also have a Japanese Noclite called Yamato 00593. And we published a paper in February on this meteorite, which showed it had biogenic-like features in it. We also have a younger sample, Shergatti, of 165 million years of age. So we have samples across the history of Mars, from the time of its early formation around 4.5 billion. We don't have a sample, but we have 4.1, 4.0, with carbonates added at 3.9 billion. We have the Noclites at 1.3, with water percolating through them at 600 to 700 million years, and then the Shergatites at 165 million. So we have a spread of materials that are available for study. Now the early crustal sample of Mars is the Allen Hills, which created all the stir in August of 96. This sample is a Milwaukee-made sample, the early period era on Mars. Now this sample, in the sample had a crush zone, and along this crush zone were these cinnamon brown carbonates, 4 to 5 times the diameter of a human hair. Now, we've studied these, and they are not high temperature. Recent studies out of Caltech show they're 18 plus or minus 4 degrees Celsius of the formation temperatures of these globules. Just as we said in 96, that they were there formed at temperatures suitable for life processes to be occurring. So, in the Allen Hill sample, we had a rock that was formed 4.5 billion years ago on the crust of Mars, the southern highlands. It was kicked off at a period of time just after Mars had water, oceans, volcanic activity, the samples there, an impact occurred. It traveled in space for 16 million years, fell in Antarctica, and resided there for 13,000 years. So here is a synopsis of the history of this rock. These globules, these are the interesting things to us. They allow us to know something about the hydrosphere and the atmosphere and any biota that might be operating on the planet. Now, to give you the perspective that we're talking about is the scales that we talk about. Here is a scale from the human at the top, 2 meters tall, down to the small, small samples that we work with. The human eye can see down to about this range. We have to use microscopes, optical microscopes, and we see in this range. Human hair is 60 microns across. Then we have to use electron microscopes, or scanning electron microscopes, or other techniques that we can go down below 1 micron. This is the nano world, and it's a fascinating world. Now, we received criticism from our early work that some of the samples that we showed were too small for living systems to be stuck inside. But let's look at this. We have a rock that had a crush zone in it. Waters percolated through it. These waters receded, and as they receded, they left their precipitants behind, and these were the carbonates. The last dregs of this precipitant was what was on the outside of these carbonate globules. John Aller and his team at Caltech proposed this is what was happening. Now, here's the Martian atmosphere. The Martian crust was in here. You had a zone that was saturated with waters that were moving through it, subsurface water that was evaporating up through it. As these fluids receded, they left the carbonates behind, evaporation. So in these carbonates, which we can determine how they were formed from their isotopic composition of the carbon and oxygen, we understand that these fluids were moving through, and as they left and trained to trap any organics, magnetites, or bioforms that may have been in there. So they are associated with these structures. So the biosignatures, if they were present, they may be retained in these secondary features. Now, our original 4 lines of evidence were carbonates at low temperature. Our critics said they were formed at 600 to 800 degrees Celsius. Incorrect. The organic components, we noted they were indigenous. They're still indigenous. The magnetites, which I'll say considerably more about, we said they were of biogenic origin and the morphology, so the structures were there. They said they were fossil-like shape. We said in the close spatial relationship, one possible hypothesis was biogenic activity. And we still stand by that today. Now, the scientific community, to understand if a sample may be a fossil biosignature, a past living biology or system, uses 5 criteria. Does the sample have body fossils? Does it have minerals that may be from biology? Are there biofabrics? Are there fossil chemicals? And what's stable isotopes? Now, as we go through this and look at it, remember this, because this is what the scientific community standard is. It's their gold standard that they seek to it. So as we go through and look at what's in these meteorites and plug these things in, remember this structure. So we wrote the paper. The paper was published in Science. It's been very highly cited. We received a lot of activity. The President made an announcement which we were not completely expecting. The chaos that occurred after this was amazing. People used a slogan against us that extraordinary claims require extraordinary evidence from Carl Sagan. Well, you might like to know that Carl was one of the 5 senior reviewers on this manuscript. There were John Cronenmeers on the stage who looked at the organics, John Brownlee, small particles, and mineralogy, Stanley Warnick, who did the microfossils and biomorphs. We suggested that Bill Schopp might be a good reviewer. He said he was too busy, did not review it, but he had been brought into the project early. You'll hear about that on Saturday. Ken Nielsen of the energy of oxidation and redox reactions from the iron oxides and all of there. And Carl from the big picture of Mars, evolutionary history and how this might have fit in there. Plus we had 3 senior reviewers of Science. They all pounded the paper. The recommendation was published with only minor changes. So it happened. Excitement, exploration programs changed, money became available for science, formulation of institutes. The data has not been discredited, and new ideas. For the first time, the scientific community recognized that we had rocks that had bacteria interacting with them. In the deep biota, we were finding bacteria at 10,000 feet, 9 to 10,000 feet beneath the crust of the earth in gold mines. They had no sunlight, nor was it happening. They were getting energy from redox reactions of iron. So these are new ideas that were there in biosignatures. Now, the structure that caught everybody's mind was this one. They said this was too small to stuff the ingredients of life into it. Well, this feature turns out to be 800 nanometers long, 0.8 microns. It has shrunk. It was shrunk probably from its original shape because as fossilization occurs, things shrink. We also had other images that some forgot. These are larger than 1 micron. This is Hodgetola Valley when you took a broken surface and you made a replica, turned it over and looked at it. And you see the other structures that are there. Some of these have been analyzed. They're silica rich with iron, and we're still chasing the carbon. Now, within the rims, the black, white, black rim is where the excitement occurred. You have an outer rim and an inner rim, and in this are minerals. There are small minerals of iron oxides or magnetites.